we were looking at the requirements of memory management, right? And we have already discussed the brief idea. Now we will go in depth, right? So let me just share these slides with you. And I have already uploaded the slides for this entire chapter on the folder, right? So it's better that even you can download and you can refer to it, right? So we'll continue in that manner, right? Okay. So we were looking at the requirement of addressing, right? So whenever you are relocating your process, the addresses will have to be updated, right? And that has to be done at runtime, basically, right? And that is why whenever we have a process, right, process is usually having logical addresses, right? Because if you are storing physical addresses in the process, relocation would be difficult, right? So that is why we usually try to store logical addresses, right? And at runtime, you translate the logical address to physical address, right? That is the process which is called address translation. We are going to see this detail whenever we'll take up that paging and segmentation topic, right? Where we will see mapping from logical address to physical address, right? Okay. So this we have seen. Protection, we were discussing yesterday. Protection is required in two ways. One is you should protect the access to OS area or kernel area. That is one thing. And the second protection is required between processes. So my process should not interfere with the data or stack area of the other process. Yes, if you are having a shared data space, it can be accessed, right? But if it is a private address space of that process, right, that should not be allowed, right? Otherwise, what if you allow that, right? And that process is having malicious intentions, right? It might corrupt the other process, right? So that's why it is not generally allowed, right? So again, who ensures this protection? It is a combined job, OS as well as hardware, right? Mostly it is the role of hardware because hardware knows the memory addresses, right? So that's why it is the job of hardware. Okay, fine. We have discussed this statement yesterday. If you want to satisfy relocation, protection becomes difficult. Why? Because whenever I shift my process, the addresses change. And so that is why you will have to provide protection once again to a new memory address, right? So protection has to be repeated every time you relocate, right? So a lot of time of your CPU gets spent on just providing protection, right? So that is again an overhead, you can say. Fine. Okay. Now we will focus on sharing. As I told you, ideally it is more you can say efficient to allow each process to share the same copy of the program. I gave you the example of MS Office application, right? So if you have a same MS Office program or MS Word program, it can be accessed by multiple processes, right? Suppose you are having 3 documents open, so all 3 are actually using the same program, right? Because if you don't do this, then lot of memory would be wasted by duplicating the program, right? So that's why it is not acceptable. Okay. So processes that are cooperating on some task may also need to share data structure. We have seen this, right, in producer consumer problem, right? So this is the same example. Are you clear up to this, up to sharing? Right. So we have seen 3 requirements. Now we'll go for the 4th one, right? Okay. So logical organization, I gave you the example yesterday, that is programs are written in modules, right? Because that is the approach we use. Even in software engineering, we design the software in modules, right? So any program, be it a software or any other application, it is written in a modular manner. But how it is going to be stored ultimately? It is going to be stored in linear fashion, right? So how that mapping works, right? How to map between the modular structure with linear storage, right? That is what is called logical organization. Fine. And how do we manage this? I think some of you asked this question yesterday. So the way for doing this is, as I told you, the CPU will always generate logical addresses. Whenever a program is created, CPU always generates logical addresses, right? And logical addresses are mapped to physical addresses or actual memory at runtime, right? This is how this entire process works. Okay, because is it possible to assign exact memory addresses at beginning whenever you are creating the process for the first time? No, right? Obviously not. Because if you do that, then what restriction you are putting on the system? Suppose you have said that my program will, or this line, this particular data will reside at 50H location, right? So when you relocate the program, right, then it will be a problem. Okay, so you can't assign static addresses, right? You can't assign physical addresses from beginning, and that is why all the operating systems which we are having at present are relying on logical addressing mechanism, right? But yes, that adds to the complexity to the memory management, because what we have to do, whenever you encounter a logical address, right? Suppose you have a jump instruction, so jump to, let us say, XYZ location, right? That is, XYZ is a logical address. So when you actually jump, what you need to do? Convert that XYZ into physical address, right? So that mapping, or you can say address translation, that's what we call, is required. So overhead is present, agreed, right? But efficiency will be better. Are you following this? Right? So mapping between logical and physical addresses are required, right? We are going to see this in detail, very much detail, when we will see paging and segmentation, right? That is coming up. Okay. Physical organization. Now over here, we are discussing the types of memories. You all know this, right? We have two types of memory, main memory and secondary memory, right? What is the benefit of main memory? Faster access. What is the drawback? It is volatile, right? What is the advantage of secondary memory? Bulk of space, right? What is the disadvantage? Slowness, right? And as main memory is limited, right, and secondary memory is huge, okay, so the challenge is how to accommodate a large process. What if your process size is larger than even main memory space, right? For that, the solution is virtual memory, that we are going to study in chapter number 8. Right? Virtual memory says that we have ample of space available. As a programmer, you can imagine that you have infinitely available memory, right? At least up to the secondary memory. That's what I can say, right? And the addresses are generated in such a way that you might be referring to the secondary memory location, but it will feel like you are working with main memory. Yes, it does not require whole process to be loaded at once. That's correct. If this statement holds what Chintan has written, then only virtual memory scheme is practical. Because if you are setting a constraint that my entire process has to be loaded in main memory, then you are losing a lot of you can say advantages. Fine, because if you are occupying entire main memory space with your one process only, then what is the advantage we are losing? It will become which kind of system? If you are just loading one process, yes, it becomes uniprogramming, right? That is not acceptable, right? So that is why virtual memory scheme has been designed, right? So that you can load your process partially. Yes, multitasking is not possible. Good, right? So what is memory management's job when we are having physical organization, right? That is written in the last statement. Flow between main memory and secondary memory needs to be properly managed, right? So what do we mean by this flow? It is swapping. Remember, we have to swap the process out and we have to bring the process in once again, right? So that swapping is an area of memory management again. It is not the area of process management. OS has number of modules like a software. There is a file management module, there is a process management module, right? There is a memory management module, right? This is the area of memory management module. Okay. So are you clear up to all the requirements? We have seen total 5 requirements, right? Okay. It is very easy to understand as well, right? Okay. Fine. Let us continue with the next method in our path, that is partitioning, right? What is the basic goal of memory management unit, or MMU? That's what we call as, right? Basic goal is we have to bring a process into main memory, right? And this is again which kind of scheduler or which kind of dispatcher? When to bring a process in main memory? It is LTS. Remember? Long-term scheduling, right? So scheduling and memory management are related. Can I say that? I hope you can find the mapping over here. Right? Every topic has a relation. Process is actually spanning across all the topics, right? Whatever we'll see, maybe it is a file management, IO management, process is going to be there, right? So you can say process is a common aspect. Okay. So which are the different ways in which we can partition the memory so that efficiently we can allow the access, right? So partitioning is one of the most important memory management technique, right? Let us go in detail with techniques. Now, some of the techniques are in this chapter, chapter 7. The other techniques, last 2, are present in chapter 8, right? So once we will introduce virtual memory, we will cover the remaining 2. These 4 we will cover in this chapter, okay? So fixed partitioning, right? As per the name, what should be the method of partitioning? Yes, we have to divide the memory into what? Fixed size partition. That means initially we will say that every partition will be of, let us say, 2 MB, right? Or every partition will be of 8 MB, right? So that cannot be violated, right? That is a fixed partitioning scheme. The second method says that it is dynamic. That means based on the process requirement, right? Suppose my process requires 8 MB, I'll allocate a partition of 8 MB. If my process requires 20 MB, I'll allocate 20 MB, right? That is called dynamic partitioning. So fixed is generally decided at earlier time, while dynamic is decided at runtime. That is the difference, okay? Then comes paging. Paging is again a method like fixed partitioning only, but in this case, the partition sizes are very small, right? Partition sizes are very small. If I give you the example, you have your notebooks, right? So notebooks have 200 pages, right? Every page can store a limited amount of text, can I say, right? So that is the real example of paging, right? While instead of a notebook, if you take example of a register is of very high volume, right? Where the partition sizes are larger, right? So you can compare register with fixed partitioning where the size of partitions are larger because page sizes are larger, right? If you have a muster or register, the size of pages are larger. While if you take example of a notebook is having less capacity, okay? There are advantages of paging. There are disadvantages also. We are going to discuss that. But remember, paging is a very popular technique, right? As far as the latest Windows are concerned, they are also using paging techniques, right? In some of the ways, okay? Another method is called segmentation. So, yes, what is the criteria to decide if it is simple paging or fixed partitioning? Yes, if the size of partition is larger than some threshold, right? Generally, the system set a threshold, right? Then it is fixed partitioning, right? While page sizes are very small, right? We'll see the examples, so you will be clear with this, right? Okay. So segmentation actually was designed after the object-oriented programming was introduced. Because in object-oriented programming, what do we have? Modular structure, right? So if you say that my program is having 3 modules, right? If you want to map it onto the memory, how many segments you require? If you're having 3 modules, you can map them to 3 segments, isn't it? Right? So depending upon the modules, you can decide the segments, okay? So segmentation technique became popular because nowadays we are having modular program structures, right? So again, we'll see pros and cons of this method as well, right? So paging and segmentation, both are having its own advantages, disadvantages. We will summarize after studying all the techniques, okay? Let us start with fixed partitioning today, right? Okay. If we assume that OS occupies some fixed portion of main memory, that means what? I am assuming that suppose I am allocating the fixed partition size as 8 MB. Fixed partition size is 8 MB. So I am assuming that within 8 MB, my kernel can be occupied, or my kernel can be stored, in other words. Okay. So even the kernel will get the same space, right? Or the other strategy can be you let the kernel occupy the space, and then whatever is left, right, you divide that into equal partitions. Are you following this? Right? I'll repeat it once again. If you assume that your kernel is occupying some fixed portion, let us say 10 MB, okay? So whatever is total main memory space minus the kernel, right? You will be left with, let us say, X. Now you divide that X into equal size partitions, okay? Whatever is the remaining space, you divide into equal size partitions. That is known as fixed partition size, okay? This is the definition. Partition the available memory into regions with fixed boundaries. Understood the definition? Right? Boundaries are fixed, sizes are fixed. Okay? Now, there are two methods under this category. The first is equal size, simplest method. Suppose you are having 100 MB of space, and if you say that my each partition will have 10 MB, so how many partitions will have? Very simple question. 100 MB available space, every partition size occupies 10 MB. So yes, 10 partitions, each of 10 MB, right? This is a very simple technique, isn't it? We don't have to think much. Just find out what is available space, divide that into equal size, okay? Okay, why the boundaries should be fixed? Yes, actually boundaries over here means it is size, Urjit. It is just written in definition. Right? So don't confuse with that, right? Yes. It is just a definition, so that's why I'm covering over here. Right? Ultimately, size is what matters over here. Right? Okay. Other method is unequal size, right? Because can you give me a disadvantage of equal size partitioning? Can anyone think of that? If I am going with every partition of 10 MB, right? What may be the drawback? Think and answer. Memory wasted. Very good. Yes, that's correct. Yes, Daniel has written the other point. Why a large size program might not fit. Some process 12 MB, correct? Yes, yes, exactly. So there are two extremes, right? Suppose my partition size is 10 MB and your process only requires 2 MB, right? So what will happen? You have to allocate the entire partition, right? So remaining 8 MB, although it is free, but it is wasted, right? Got the first point? If you have a very small process, that wastes the space, right? Extreme point on the other side is, if your size is more than 10 MB, now you will have to deny that process actually. Because right now we are not having virtual memory scheme. So what we are assuming, if a process has to execute, it has to be loaded completely, right? When virtual memory scheme is not present, right, what is the assumption? If a process has to execute, it has to be loaded completely, right? Can I load a 12 MB process over here? The answer is simple, no. That means that process cannot execute. That is not allowable, right? You can't deny a process actually, right? So this is the problem of equal size, and that is why what we can do to solve this, have some partitions of small size and the other partitions will be of large size, right? So, or virtual memory, yes, that is another option, right? But in earlier operating systems, virtual memory scheme was not introduced, right? So they were relying on this simple techniques, right? Okay, so let us continue with this now. If I go with equal size partitions, right? Let us see the method first. any process whose size is less than or equal to the partition can be loaded. Clear with the rule? Right? Because in exam, if you are given, let us say, memory space, right? And if you are asked that how will you allocate, in which order, right? So you'll have to pick that. In exams like GATE, this kind of questions are being asked, right? So you should be prepared for this kind of questions. Fine. Okay. The operating system can swap a process out, right? If none are in the ready or running state, right? I hope you agree to this. If you are having 10 processes, all of them are blocked. So what is required? Swapping, right? To bring a ready process inside. Okay. So again, in this case, see, you can easily see over here, OS is occupying the same partition size, right? But the another way is also possible. As I said, you let OS occupy the space and then you see the remaining space. Whatever is remaining, divide that. Okay, so there can be two approaches. This is a simpler approach, we can say. Problems. As we discussed, a program may not fit a partition. Right? That is the first point. Okay, that means if the size is larger, then it will not fit. So, if virtual memory is not available, what is the only solution? If virtual memory is not available, what is the only solution? You have to overlay the memory space. That means, suppose currently you are given addresses of 50 bytes, right? And let us say your process is of 60 bytes, right? I'm just talking in terms of bytes, not in MBs, right? So what will happen to remaining 60? What you will do is you will load first 50 bytes, right? And then process, right? And after the first 50 bytes are processed, what you will do? You will overlay the existing 50 bytes with the new 10 bytes. Overlaying means overwriting. Overlaying means overwriting. So that means if you can't load the complete process in the same region, what you will do? You will load a part of that, right? And when the part of the process is executed, what you will do? You will bring in the remaining part, and that remaining part will overwrite the existing process. Is this efficient? Overlaying or overwriting? No, because you might lose an important part of your process, right? And another cost is, yes, that's what I was pointing to. If there is a jump instruction, then it won't be possible to use this method, right? Overlaying will not support that. Janil, I hope you agree. Can't we load the remaining in a new partition? Yes, but then you will be occupying a large space for a small area, isn't it? So that is again a wastage, isn't it? So overlaying is one solution, I am saying, not an efficient one. Okay, that is why people go with either dynamic partitioning or you use virtual memory. Right? There are two options. Clear with this? Right? Okay. Let us now focus on efficiency. In case of fixed partitioning, efficiency is not present. We have just seen that, right? Any program, no matter how small it is, it occupies the entire partition, right? And this is one of the key points which you should know as a part of the OS. Yes, I'll explain, Urjit, just after 2 minutes. Right? Internal fragmentation. Right? Suppose you are having 10 MB partition, right? Out of 10 MB, you are just occupying 2 MB.